Today we're solving LeetCode 1306, Jump Game 3. And in this video, the focus is not just the solution. We're also trying to understand something more useful. How to look at a problem and notice the pattern early, how small keywords in the statement quietly point toward the approach, and how to actually follow the flow step by step instead of guessing. All right, let's start. Before we jump into the problem, quick analogy for the people who are into Attack on Titan. If you're not interested in that, you can skip to the next timestamp where we start the actual problem. There's a moment when the scouts enter unfamiliar territory with multiple hidden paths. Some paths move them forward, some pull them back, and some bring them back to places they've already been. At one point, Levi points out something simple. If we keep returning to the same places again and again, we won't make progress. So they start tracking where they've already been, not because the world is complex, but because repetition traps them in loops. And that idea is exactly what we use here. Now moving into the problem. We are given an array and a starting index. From any index I, we can move to two positions, I plus r at index I or I minus r at index I. And the goal is simple. We want to check if we can reach any index where the value is 0. Now notice something here. When a problem talks about jumping from one index to another, multiple possible moves from a position, reaching a target from a start, revisiting states again and again. That immediately gives a direction. So let's ask a simple question. What is this really? Are we just moving inside an array, or are these positions actually connected in some way? Yes, this behaves like a graph. Each index is a node, and each node connects to at most two other nodes, left and right. So now the question becomes, can we reach any node whose value is 0? And one more important thing shows up here, cycles. Because from one index, we can come back to a previous one, which means without tracking where we've been, we can get stuck in an infinite loop. So we keep a visited structure. Now let's build the idea step by step. Imagine we are at index 5, and r at 5 is 1. We simply ask, where can I go from here? Only two places, 4 and 6, nothing else. So what we're really doing is starting from one position, exploring all connected positions, and checking if any of them leads to 0. Now let's take the example. R is 4, 2, 3, 0, 3, 1 to start is 5, friend. And as we go through this, there's a visual walkthrough on the site that shows exactly how the queue changes at every step, how nodes are visited, and how BFS spreads level by level. That makes it much easier to actually see what's happening instead of just imagining it. We begin with a simple queue. It contains only one value, 5, because that's our starting point. Now BFS always works in order. So we take the front of the queue, that is index 5. We check, have we already seen this? No, so we continue. Now we check the value at this index. It is not 0, so we move ahead. We mark 5 as visited. Now we generate possible moves. From 5, 5 plus 1 becomes 6, 5 minus 1 becomes 4. Both go into the queue. Now queue is 4 and 6. Next, we process 4. We check, is it visited? No. So we continue. Value at 4 is 3, not 0. We mark it visited. Now we generate moves. 4 minus 3 becomes 1, 4 plus 3 becomes 7. 7 is out of bounds, so we ignore it. We keep only 1. Q becomes 6, 1. Now we process 6. Value is 2, not 0. Mark it visited. Now moves, 6 minus 2 becomes 4, but 4 is already visited, so we skip it. 6 plus 2 becomes 8 out of bounds again, so nothing is added. Q becomes 1. Now we process 1. Value is 2, not 0. Mark it visited. Now moves. 1 minus 2 becomes minus 1. Invalid 1 plus 2 becomes 3, so we add 3. Q becomes 3. Now we process 3. And this is the key moment. We check the value. It is 0, so we stop immediately. We found our answer. So the path we followed is 5, 4, 1, 3, and that leads us to 0. Now moving into code. The idea here is simple. We translate the logic we just walked through into steps the computer can execute. We need something that explores level by level. So we use a queue. In Python, this is done using dkey from collections because it allows fast operations from both ends. Next, we need to avoid revisiting the same index again and again. So we use a visited set. This ensures every index is processed only once. We start by putting the start index into the queue. Now we keep running a loop until the queue becomes empty. At each step, we take the front element. That becomes our current position. We check two things immediately: if it is out of bounds, or if we have already seen it. If yes, we skip it. Then we check the important condition. If the value at this index is 0, we return true right away. Otherwise, we mark it as visited, because we don't want to process it again later. Now we generate the next moves. We calculate I plus R at I minus R at I and add both into the queue. This continues until either we find a 0 or we finish exploring everything. Now complexity. Let's connect this to the constraints. We are told array size can go up to 50,000 values. Always stay within valid index range. Start is always valid. So what does that mean? In the worst case, we might visit every index once, because visited prevents repetition. So time complexity becomes big O of n. Even though each index can create 2 moves, each index is still processed only once. So total work stays linear. Space complexity. Visited set can hold up to n elements. Queue can also grow up to n elements, so space is also big O of n. And that's the complete idea. We are simply treating an array like a graph. Each index connects to 2 others, and BFS helps us explore safely without getting stuck in loops. If you like this way of breaking down problems using patterns, intuition, and visual understanding, you can check out the website for more problems like this and subscribe for more. Thanks for watching. Tatakai.